Welcome back to the video of my channel, pep_exe. Today we're going to look at more volume and surface area problems. So here's question 1. We need to find the missing side of each solid below. So let's just start with part A. So for part A, we have a hemisphere, or in other words, it is a sphere cut in half with a radius r and a surface area of 27 pi centimeters squared. First, I'm just going to derive a formula for the surface area of this hemisphere. So from the diagram here, we can just divide the surface area into two parts, the green region and the yellow region, based on the diagram on the left. Notice that the green region, the area of the green region will be half times the surface area of a whole sphere, which will be 4 pi r squared. Let me just fix that writing a little bit. And on the other hand, the area of the yellow region is actually just a circle, and this formula will be pi r squared. And simplifying this, you'll get 3 pi r squared centimeters squared. Oops, not the centimeters squared. And we can set this equal to 27 pi centimeters squared, given by our information here. And we can divide 3 pi on both sides to get r squared is equal to 9 pi centimeters squared. Well, not the pi, because we already divided it out, so it will just be 9 centimeters squared, which will leave us if r is equal to 3 centimeters. Notice that we don't include negative 3 centimeters, which is also a solution, since we're in the world that we're supposing positive dimensions and lengths. Alright, so for part B, let me just erase a part of this a bit. Oops. So here we have a composite figure made out of a cylinder on the bottom and a cone on the top. And its total volume will be 540 pi. And we need to find the length of this x here. Now perhaps we can just generalize a volume for this composite figure. Notice it will be the volume of a cylinder, which is pi times r squared, which will be just x squared, times its height, which will be 12. Plus the area of a cone, the volume of a cone, which will be a third times pi times x squared. Notice that the cylinder and the cone have the same base radius because the surface of the cylinder actually fits in perfectly with the surface of the cone. So thus it will have a same radius, or basal radius I should say, times 9, which will be our height. Simplifying this, you get 12 pi x squared plus 3 pi x squared, which will be 15 pi x squared, which we can set this equal to 540 pi given our information. And therefore we can divide both sides by 15 pi to get x squared is equal to 36, and therefore x must be 6. And for the last question, we have a prism with our base being this insane polygon, and is being extended by a length of 100 meters, and its volume will be 370,000 meters cubed. And notice that the base area is actually made out of several squares that are joined together. So what I would do in this case, I'm just going to divide this into several regions, and I'll be right back after I'm done. Alright, so here we have several regions, that are actually squares, since all of these sides are equal. And notice that all of these sides of the squares are equal to each other, and therefore each squares must be congruent. And what that tells us is that we can find the area of the base by counting how many squares there are and then multiplying by the area of one square. And if you count the amount of squares in this in this whole area, that will be 37. And the area of one square, and notice in this case the center of a square will be a, so that will be a squared. And let me just confirm this, that there are indeed 37 squares. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, and 37. So there are indeed 37 squares here. So the volume of this prism is actually the base area, which is 37a squared, multiplied by 100 meters. And we know that this is exactly equal to 370,000 meters cubed. And we know that we can simplify the volume in terms of A as 3,700 A squared meters squared. And dividing 3,700 on both sides, you get A squared is equal to 100 meters. Let's see. So of 100 meters squared, that's a units, and therefore we have A being equal to 10 meters. And that's the answer. So that's the answer for question 1. Let's jump into question 2. Alright, for question 2, we need to find the surface area and volume formed by the net of each solid below. So we're given 3 nets, and we're just start off with part A. And straight off the bat, you can notice that this is indeed a triangular prism, since you have two identical faces in the form of triangles, and we have the 3 rectangles to join in the other sides. The other faces of this prism. So let's start off with the volume. The volume will be the area of the base times the extension length. Now the area of the base will be the area of a triangle with base 4 and 6. So that will be half times 4 times 6. And after that, multiply by another 10. And therefore we get 120 units cubed. For the surface area, we need to do a little bit more work. So let's just consider one of these triangles, and we'll just draw it on the side here. So it is an isosceles triangle with base 6 and height 4. So from the diagram, we have drawn a line that is perpendicular to the base. Now it is pretty easy to see that this red line is indeed a perpendicular bisector of the base, which means that it divides the base into 2 equal parts, and those parts will be 3 and 3. And we can just draw another triangle, in this case a half of this triangle, which will be this part right there. So it has base 3 and a height 4, and it forms a right angle there. And it is easy to see that by the Pythagorean theorem, we know that this hypotenuse will be 5. So what that tells us is that these lengths will be 5, and therefore there's a 5 and 5 there. Alright, so we're now ready to calculate the surface area, which will be 2 times the area of the base plus the perimeter of the base times the length of extension. So for the area of a triangle, the area of the base, it is an area of a triangle. And for the perimeter of a triangle, notice that it has side lengths 5, 5, and 6, and therefore its perimeter will be 16. So that will be 16 times 10. Solving this, you'll get 160 plus, notice that these and these will cancel, so we have 24. So 160 plus 24, that will be 184 units squared. Alright, for part B, we'll notice straight off the bat, yet again, we can notice that this is a net of a cube. Because notice that all of the faces of the 6 faces are actually congruent squares. And what that tells us is that we can calculate the surface area by the number of the squares here. In this case, there are 6 squares, so 6 times the area of each square, which will be 25 meters squared, given here. So that will be 150 meters squared. For the volume, we need to find the length of each side of the squares, and that is not hard to see. It is actually 5 meters. This is obtained by taking the square root of 25 meters squared, by the way. And for the volume, it is the length of the side of this cube cubed. And this is pretty easy to see by generalizing this formula from the volume of a prism. So this will be 125 meters cubed. Alright, for part C, this is quite interesting. Since by the shape, we know this is a net of a cone, and a cone after it's folded will look a little bit like this. So let me just draw this line right there. So it has a base radius of 5 from here, and it has a side length of 13. Now let us consider the triangle here marked in yellow. So let me just draw a proper triangle. So it forms a right angle. It has side lengths 5 and 13. And you can use the Pythagorean theorem to find the height of this triangle being equal to 12. So this is equal to 12 there. And therefore, we can calculate the volume of this cone by knowing that the fact that the volume of a cone will be a third times pi times r squared times h. So that will be a third times pi times 5 squared, which will be 25 times 12. And I'll let you guys do the arithmetic there. You can substitute an approximation for pi, or you can do whatever you want. So next, we can find the surface area, which will be pi r times r plus s, where s is the side length of the cone, which is 13. So that would be pi times 5 times quantity 5 plus 13. And again, I'll let you guys do the arithmetic there. And therefore, this ends question 2. Alright, here's the final question. This figure shows a cross-sectional area of a pool with a length of 10 meters. So it is extended to this way, 10 meters long. The depth of the pool ranges from 1 meter to 2 meters as shown in the diagram here. And for part A, if the pool were to be fully completely filled with water, or filled completely with water, find in centimeters cubed the volume of the water needed. And that is actually very simple. We need to just find the volume of the pool itself. So the form will be, well, notice that this pool is in the shape of a prism, since we have a base area and it is being extended 10 meters. So that's one of the main characteristics of a prism. So the form will be the area times the length of extension, and this area is actually a trapezoid, which means its formula for the area would be 1 meters plus 2 meters, which are the lengths of the parallel line segments, divided by 2 times 5 meters, which will be the height of this trapezoid. And then all of that multiplied by 10 meters. And that gives us 75 meters cubed. Okay, so this is part A. Well, for part B, from the amount of water in part A, which I've already found, how many cylinders with base radius 5 centimeters and height 10 centimeters could it completely fill? Now the keyword is completely here. Note that we only count cylinders that are completely filled with water. If we have a cylinder partially filled, we can neglect that from our answer. So what that tells us is that assume that we have a number of cylinders that are completely filled, and then we have one cylinder that is actually halfway filled, and we can just neglect that from our answer. We can just not count that in our answer. So that is basically what it's telling us here. Now notice here that the dimensions of the cylinder are in centimeters. So it's probably best to convert this into centimeters cubed, which will be an insane number. It is 75 million centimeters cubed. However, this will be very essential later. So for part B, well, we can just compute the form of a cylinder, which will be pi times r squared times h. So pi times 5 centimeters squared. That's from our information above, times our height, which will be 10 centimeters. And this will give us 250 pi centimeters squared. Alright, once you have got the volume of the water and the volume of one cylinder, you can calculate the number of cylinders that it could completely fill by the volume of the water divided by the volume of one cylinder. So that will be 75 million centimeters cubed all over 250 pi centimeters. Oh, sorry, this is supposed to be cubed. There we go. And if you input this into a calculator, you'll get approximately equal to 95,492.96586. Now don't get too excited yet, because this is not exactly our answer, because notice here that we only count cylinders that are completely filled with water. And if we imagine this as the number of cylinders, we can see that there are, so I'm just going to make some weird circles to represent cylinders. So there are 95,492 of these, and then we have one that is almost completely filled, and we can just determine that from the decimal places there. And just like it tells us on the question, we can neglect this partially filled cylinder. So our answer will be 95,492. So that's the number of fully filled cylinders. Alright, so that's it for this video. So thank you guys for watching this, and please subscribe and goodbye.